one of the key themes of this workshop is, right, there's a need to spend more time and pay more attention towards applications in neuroscience. Because there's huge amount of work happening in basic science, but look at the clinical applications of neuroscience, there are not, they're not very impactful, right? Because if you look at any of the major diseases, unless it is an infectious disease or a problem which consists of, a simple surgical intervention, we can't say we have cured any of the major diseases. We just manage, we just, right, give palliatives and things like that. So I don't know if this comparison is valid. People may not like, especially biologists may not like it. But if you look at the relationship between physics and engineering, in physics you have the basic laws, right, and then which smoothly extend over to the engineering or applied domains. And all the applications sit on the foundation of the basic laws, the basic equations which come from physics. Whereas in neuroscience, it's not the case. I mean, in fact, very often we don't even know what are the fundamental laws of the brain. We're not able to distinguish between the basic laws and the details. So therefore, there is a simple disconnect, and which is what Dr. Lata was talking about in her presentation this morning. So I just want to, have a kind of open debate about why is it like that? Should it have to be like this? Is it possible? Because there's a social problem, sorry, right? It's not an academic problem. So shall we talk about it? I mean, that's all. I just want to set the ball rolling and let the panelists, kind of continue. And I would like the audience also to contribute. Right? It should be a totally interactive session. Let's go ahead. Anybody? Bapi, Raju? Lata? Hello?
Yeah.
Hello?
Oh. Yeah, so somebody can kind of pitch in.
Yeah. Stephane wants to say something.
No, Prof, you can go ahead. I'll join.
Yeah, so I guess the question that we wanted to address is how are some of the models of specific systems? We have a variety of models which are successful at different scales, explaining neural recording, synchronization patterns at one level, and the other is at a higher level. For example, models of attentional tuning, salience. However, I guess the issue is when it comes to most of these give us some sort of insight into how systems in a localized fashion they function, and what can we infer at the localized level, and typically in an average picture of what happens across participants, right? In some sense, there is a lot of individual variability. Biological systems are specialized or notorious for variability, right? And variability is a whole debate on the functional or systemic significance of such variability. But this variability also leads to complexity in terms of, you have an average picture, but then how do we use this to talk about an individual condition, right? In a clinical setting, for example, the manifestation of, this, you have this generic name called dementia, right? Alzheimer's dementia and Parkinsonianism. But these are only some certain clinical conditions like autism have acknowledged that this is a spectrum, right? And there can be a huge variation in how this manifests. But in conditions like dementia, it is still considered, people are looking for general patterns, whereas individual participants, it is only much later. For example, in dementia field, people have segregated behavioral variants of dementia, which is now called frontotemporal dementia. So which manifests based on issues with degeneration in the frontotemporal. Although the origin of this could be disruption or tangles in the temporal lobe and in the hippocampal area, but they are spreading toward other brain regions. And depending on what the progress is, you have different manifestations. So memory loss, loss of conceptual, this semantic dementia. So there are multiple variants of a single thing called dementia. Dementia, which is popularly considered loss of memory, right, starting from hippocampal system. So so this variability also comes from, I have a feeling, individual experience as well as individual anatomical variations, right? So so when it comes to applications in clinical domain, useful applications in clinical domain, how do we bring these ideas to a person-specific characterization? It's a big challenge, and I think that's where I'll stop and perhaps let other people also pitch in what they think.
Okay, thank you, Professor. Dr. Lata, you are saying something that in the morning that so there is a challenge from a social, from a organization behavior point of view, which neuroscience is not addressing. So can you make that statement in this context once more?
Yeah. Hi, I was just talking about that in the morning, where I was emphasizing on how does neuroscience apply readily to non-clinical settings. So, I mean, clinical settings have been talked enough, and there's huge literature which all of you experts are, publishing around it. We're looking at what kind of solutions can you give from neural basis or brain basis when it comes to real-time social problems.
Can you give examples like?
Examples can be just individuals' performance in a team setup. The team need not be a group. It can be just 2 to 3 people. The performance, productivity, efficiency, motivation, volition, or there are so many things. The individual need not be a deviant, disorderly person, non-clinical setup, but goes through several of these the so-called anomalies at some point or the other on a day-to-day basis too, though it doesn't term itself to abnormality or disorder or dysfunction, but it is definitely a dysfunction in a temporary basis. Maybe it's I'm not suggesting any mood disorders or anything, but it is there in every one of us, and that affects our day-to-day life too. We need not have a critical, acute disorders to get your neuroscience attention. So
Right.
being a very normal person, I mean, the so-called, at least the societal norms of acceptance of what is normality, we all have still so many other problems other than just the clinical setups and its solutions. So any thought, any inputs on neural basis, brain basis solutions to the real-time organizational, social, and people's problems?
That's right. Actually, if you go by DSM-4 or any of these psychiatric manuals, pretty much every one of us will look like psychiatric patients. So
Absolutely.
that's not very helpful, right?
Every symptomatology suits me.
Yeah.
I felt, I mean, of course, the deviance is something which keeps changing, and it's pretty dynamic depending on culture, geographies, or biological makeup. All of that is true, but then I would like to see more application of directly going for neural and brain basis solutions for the real-time situations, business scenarios, organization scenarios, administrative scenarios, or academicians like us who are into science management. By organizing some of these meetings, we are nothing but we are managing some of our mind share. And we thought that we can manage for online meetups. So there are so many things, like we were not I mean,
That's
some
right.
of us who were talking were not audible.
So can we move, Stephane?
What does it go through? So how does the brain reorganize, adjust, adapt, or people just quit and just leave the meeting? There are so many things. So how about the problems in day-to-day lives than just clinical setup? That's one of my concern.
That's right, Lata. That's a very good point. Stephane, you are saying something in the chat box. Hello, Stephane, can you hear me? Hello?
Yes, I can hear you. I just want to write things down. Comments? No, yeah, I didn't want to bother people. So, but because the complexity, I also asked. We ask ourselves all the time: is complex enough? We have a lot of problems. In our case, to figure out what is the sufficient complexity of the model we have and what is too complex, what is overfitting and what is not complex enough, so that how can you know which behavior you want to take into account and when is it sufficiently complex and when is it not. So we have several programs where we look at quantum mechanics directly at the interface level in the brain. We have a lot of things going on at very small scales, a lot of things going on at very large scales, but what we don't have is a way to bridge these two scales. So to me, I don't know really in the real field of neuroscience, because I'm only a mechanics engineer, so I do applied math. I don't know what's going on really, but having read and listened to a few people talking about this, I have a feeling that there is complexity that is so huge that if we want to take everything into account, like in the Blue Brain project at EPFL, I mean, we may lose ourselves in details and not find out what's really important. And so that's the first thing. The second is about model order reduction. So that's something we use a lot in our field. Essentially, proper orthogonal decomposition, singular value decomposition. It's not groundbreaking as a method, but sometimes it can be very useful, in particular if you have nonlinear manifolds and if you want to actually fit the nonlinear manifolds, which probably in our case we have time series that are so complete, like basically predict what's going to happen next, or we would like to classify. So we look at a certain pattern, and that pattern we want to know, is that going to be some epileptic crisis, or is that going to lead to case A, case B, and we'd like to be able to read this from that. So maybe what I was thinking is, like language, if we could find out what are the common blocks in language, so is there a common denominator to all languages that we can say this is a structure, Chomsky was saying, the linguist. So if you split things into small boxes, what are the smallest boxes that you can split it into? And is that a basis, like a vector space that you can then create the whole range of possibilities from that small set of bricks? So I don't have a clue if we can do anything like this, but from a mathematical point of view, it seems like a beautiful idea to try to think what are the key building blocks, at what scale, and then if we could find this out, and we could try to project what we read on an EEG on that basis, and then say, okay, there is a component that goes in this direction, another one in that direction, and then we have different parameters, which are the coefficients of the projection, and can we learn something from this? And that's it. That's all I wanted to say.
Yeah, thanks a lot, Stephane. I think you have a lot of important points here. Because one thing you stressed on is the problem of scale, right? How do you work across these multiple scales, right? In engineering or physics, you have this concept of abstraction, or encapsulation. So in one context, an object can be treated as a point mass. In another context, you treat it as an extended object and you use FEM methods. But you know exactly when to do what. In neuroscience, we don't have the distinction. And especially if you talk to hardcore neuroscientists, they think that unless you do Blue Brain project kind of a simulation, you won't understand brain. But actually, it's the other way around. If you do Blue Brain project kind of simulation, you will definitely not understand brain. It's just a point by point reproduction. There's no abstraction. Without abstraction, there's no modeling. There's no understanding. So I think there's a very fundamental problem of how we look at brain. There's a poverty of concepts. I think we don't have the right concept. Once you have the right concept, engineering becomes very simple. It's only computation. I mean, computation is for, it's routine stuff. It's a conceptualization and formulation that is a hard problem, right?
Yes.
And after that, it's more or less a routine. I mean, figuring out the Newton's laws is a hard problem. Once you have it, calculating the orbits is not that hard. But whereas with the brain, unfortunately, there's a paradoxical situation where there is an apparent sophistication without deep insight. Right. So I think that is the reason why we are not able to treat real world problems. And everything is a big unsolved problem. I mean, take stroke rehabilitation. There's so much variability from subject to subject, from patient to patient, and it becomes a joke when you actually start trying to treat a patient. I mean, take Parkinson's and how you give prescribe drugs. It's just, it's almost like astrology or voodoo black magic. I mean, there's no logic to it. Why people do what they do. So I think this kind of an abstraction is lacking in neuroscience, and therefore all the problems that that Lata was talking about, they all seem to stem from the same underlying kind of a deficiency. I mean, I don't know why it is lingering for such a long time, but I think it has to be at least talked about, right? So Raju, Bapi, you were saying something.
Yeah, the other, while it is point well made in terms of lack of this sort of bridging sort of connectivity between different levels, and also working models at different levels of abstraction. Apart from this, what I feel, I mean, on the positive side, I think there is a realization that there are organizing principles, both spatial, temporal, organizing principles that seem to be working at different scales in almost a similar way. For example, topographic organization, and some sort of nonlinear representation of the external world on the topology of the brain. This is one principle. There's other principles of so local excitation and lateral inhibition that sharpens the signal, right? And this can work at different levels. This can work at a very low level. This can also work at the level of two hemispheres competing to process the signal. And whoever wins the competition can actually process and suppress the other. And now if you disrupt this through a stroke, for example, and you see classical manifestations of the disruption and the inhibition causing excitation in the other cortex, intact cortex, right? This is actually manifestation of the principles. I think our problem, because of the interdisciplinary nature and the origins of neuroscience, I mean, being from biology, which is typically even now considered a descriptive science, right? I mean, this is where I think there are certain bridges that need to be made, systems level thinking that typically a physics person going to engineering quickly grabs these ideas of how to use this principle to make systems that work. And what are the assumptions, what are the boundaries. We do not have this sort of a way of treating neuroscience as giving us a set of principles that are actually evolution is reworking them at various levels. One more example I want to give in this context, the recent, the Nobel Prize that you talked about for spatial, navigation, that the UCL person as well as Moser, they both have got. And so the idea there is that there is an internal representation of the space in certain form that is accessible to attractor dynamics, that that you have a discrete representation, but there is a dynamic system that can access this this sort of discrete coding of space. Now, what recently what these people have proposed, for example, perhaps there is such a representation of the cognitive space within hippocampus, and thought as a navigation in this cognitive space, right? So I think we need to try and actively look for organizing principles rather than inventing a new system for every phenomenon, right? Otherwise we'll end up with a bunch of models and systems for variety of phenomena, but there is no connecting link. Okay, I'll leave at that and see what are the reactions.
Any comments, Lata?
I think I second what Professor Raju is saying. We need more organizing frameworks. More organizing frameworks than just the representation of the way we largely understand the brain into hemispheres and lobes, and then digging each lobe and seeing which function it serves. But it cannot largely explain a lot of other functions. We really do not know where it emerges from, and nor we are very keen on emerging that, but largely managing the problems in the outer life. Then do we have to fix something in the brain? So, affective, behavioral, and social neuroscience. These things should comprise of what? What kind of manifestations and models, microscopic, macroscopic, what kind of models would or scales would serve to serve better for affective, behavioral, and social neuroscience? I think scholars in these areas can work on some of these things.
Actually, that's a very good point that you brought. In fact, you hinted upon that in your talk in the morning also. So when we talk about mind, why are we only confined to the brain? Why not look at the entire body? I mean, many people have suggested, for example, the somatic marker hypothesis, Damasio, and then a whole lot of affective neuroscience or emotional neuroscience talks about the involvement of the feedback from the body, through autonomic feedback from the body, right, playing a role in our emotional processing. So if that is the case, when we talk about what we call experience, why don't we talk about what happens in the entire body and not just in the brain? So same thing when we in group dynamics. So one thing I feel, I'm asking a question here: is it possible to rework neuroscience and make it look something like this? So like Bapi was talking about, focusing on fundamental principles or organizing principles. That's very important. So in fact, it will be nice if, at the end of maybe 10 years down the road, if somebody can work out like the 10 basic laws of the brain, right, in a neuroscience textbook. That's what you will study in the first 2-3 chapters. And after that, in chapter after chapter, you apply these principles to various systems, right, explain how they work. And then in the subsequent section, you apply them to the whole person at individual level. And same principle will explain the behavior at the individual level. Then in subsequent section, you apply the same principles at group level and how individuals interact. It's the same set of principles that are able to explain behavior from single neuron to local circuits to to systems, to individuals, to groups of individuals. I mean, won't that be great if you are able? Because that's what happens in physics, right? I mean, single atoms bouncing off each other. I have some they're just following some force fields, right? And then I have groups of atoms, interconnected, and I have molecules. Again, same story. And molecules form rigid objects. Again, same story, right? If they could form continuum, they could form rigid objects with the same story. I mean, how beautiful it is. Why can't we bring in that kind of a beauty of structure, right, into neuroscience knowledge? Why is it so different? I mean, I believe it's the same. It's just that we're not able to look at it in the right way. I mean, but people can counter it. This is what I feel must be done.
I think that's a wonderful way of looking at trying to address this question, but we really do not know
if it's possible,
yeah, because you biologists will be able to
No, we are not a biologist, unfortunately or fortunately, right? I mean, that's the reason biologists hate us. In my own department, we're constantly told that you guys don't know biology. This is not, you're not a biologist.
Yeah,
We
because
are
we really
reminded
don't
every
know.
time.
Because we talk in these terms where a kind of a solution which fits in for a lot of similar looking models.
Yeah.
It's like a mass model which can
Yeah.
be applicable to quite a few, at least, if not all. Even that might not, we really do not know whether that approach is also right or not. So specialists like you should put
I
more
don't
light on
understand.
these.
Like take, for example, systems theory, right? If you have a cascade of two systems, you just multiply the transfer functions, you get the transfer function of the whole system. It's so simple, right? And so it just scales up, right? You can have a big block diagram of systems. You just apply your series and parallel laws, and you can get the transfer function of the entire system. Why is it not possible to encapsulate like that in the brain?
No, I mean, there is a difference between engineered systems and evolutionarily evolved systems. I mean, of course, but the methodology doesn't have to be different. But I think we need to keep this in mind. However, having said that, it is parsimonious, or it is very to assume that evolution would have not would not have discovered a new mechanism every time there is a for the next population or next generation, right? It would rework the same principles, and there is a whole bunch of evidence throughout the nervous system for the reuse of principles from lower order organisms to higher order organisms, how these are modified and reworked for doing the same thing. I think one possibility is like what Nabila, I think, has said in the chat box. Invariances is a very popular thing that people try to find out what are the invariances that are in variety of systems. I think as a group, we have enough number of people, brains, to put together. I mean, say in the next couple of years, each of us put down one principle they think is working and some evidence for it. And now we list them and we see if there are redundancies, we remove and filter it down, right? I mean, this could be a fun project across 40 or 50 brains that are there currently in this meeting.
I think that's a good suggestion. We can try to connect with people, right, who think on similar lines and work out this program. Who feels the sense of urgency or see this challenge and work out this kind of program.
Yeah, Alekia has some article. If you have read it, maybe you can give a couple of lines about that, Alekia.
Alekia, please go ahead.
Hi everyone. So this is morely like semi-quantitative. So this was in work done by a group here in Cambridge. What they tried to do is they took a behavioral task and also combined it with a set of questionnaires which the researchers use for DSM, as per the DSM manual, looking at affective, social, then different aspects of psychology like anxiousness, depression, compulsiveness, and social behaviors and everything. And they try to do some kind of factor analysis and bring out the basis components which can be which can explain 3 different dimensions and combine it with various structures in the brain or various activities in the brain. So it's more or less, but it's very semi-quantitative and behavioral oriented rather than any principles or in those lines. Yeah. Hello?
Oh, that's nice. Alekia, remember about, I think 6 months or 1 year ago, we had a discussion to kind of look at all literature and collect a set of basic principles of the brain. I think we identified some 6 or 8 principles. I don't remember what the principles are. But even with the existing literature, it will be nice to just do a survey and see what could be those basic principles. Like self-organization is one thing, and so there are several other things. But
I agree with you.
yeah, actually, I want to give another example. So the thing is, it's also a question of how people look at systems, right? You can try to get all the details and piece together, like in kind of like something like in classical painting. In classical painting, you want to reproduce the object as it is with all intense detail. Right? Whereas in modern art, you try to capture the essence of the object. I mean, that's like impressionism and things like that. So similarly, so there is a study by Stuart Kaufman, who is an evolutionary biologist, right, who was looking at gene regulatory systems. So now if you look at systems biology, they try to work out all these circuits in great detail and using run them on supercomputers, things like that. But what Stuart Kaufman has done is he's just taken a general random Boolean network as a kind of a model of gene regulatory system and studied the attractors in it, right, the attractor structure and distribution in it. So the N is the number of units, which represents the number of genes, and K is the number of other genes that a given gene can influence, right? So then he has constructed random networks. And what he found is when K equal to 2, that is a given gene can control only 2 other genes, he found that the number of attractors you will have is about roughly square root of N. This is statistical analysis. And so that each attractor then represents something like a cell type. Because in a given cell, certain genes are expressed cyclically throughout the cell cycle. So that's like an attracting state of the gene regulatory system. And it turns out that the number of genes and the number of different cell types a given organism will have has actually that kind of relationship, right? So if N is the number of genes, square root of N is roughly the number of cell types you can have in that organism. Now that's a beautiful result. I mean, that's something only a physicist can think of, right? But in a typical biology fashion, people would actually collect all the details and construct huge networks and things like that. So that flavor can we bring in like more often, right? And try to understand the fundamental laws of the brain. And maybe we'll progress much faster if we can do that. But that's not easy. I mean, how do you even figure out what kind of model to work to do? There's no simple answer to that. But it's a really beautiful result. So anybody else? Anybody from the audience also can chip in. I mean, whatever you feel like. Stephane, any comments further?
I'm wondering how to achieve it in a practical way. That's what I was thinking. I looked recently a lot at what they are doing in Stanford, with the Huberman lab. I don't know if you're aware of them. I found them very, very impressive, and but they are doing mainly experiments. And I was talking to him, and he was saying that he's interested in the computational approach, trying to learn from the basics. I don't know practically how to organize such.
Yeah.
I completely agree with what you're saying. Yeah. I think it's a very smart sort of analysis of the situation, that we don't have the first principles and we're trying to complexify the whole thing. Yeah. I like it very much, but I don't know how to
it's not easy,
to go about it, basically. That's my problem. One of my problems.
So there's a question of academic beauty and all that. There's also a practical economic question. Because in the 90s, when they started the Brain Initiative in US, that's $1 billion project. We thought, wow, that's a big project. And now apparently China is pumping in like tens of billions into neuroscience. Now, what are we getting out of all that, right? I mean, I'm impressed by the funding, but what is it that you're able to give to the society in terms of actual problem solving? I mean, not a whole lot. You go to SFN, there's not much of problem solving. It is infinite analysis of I don't know what, but whatever. So I find it very weird. Engineering doesn't work with that. Right? There's a continuum from basic science to application.
Yeah, that's
a nicely streamlined process. Whereas in neuroscience,
yes, well, yeah, Andrew Huberman was saying exactly this. He was saying So for example, expose your retinal cells to a red light from that time to that time in the morning, and then in the evening do this and do that, so that your cells do not degenerate over time and you don't lose visual acuity after 40 years old and so on. So that is very, very clear about what to do. How do you stay performant? How can you do make up your life so that you have the noradrenaline stress level that is then compensated by dopamine, so that you feel this little bump of energy because you have achieved a small goal, and then you go to the next small goal, and then you get that stress, but the dopamine comes back again to give you more. So he's studying these things in the lab, mainly on humans and also on rats, but on humans in particular, with some virtual reality labs, which I think is quite unique. And then, so it's very practical, and that's also what I don't know. How do we take all these theories that maybe we don't even have in order to make real progress and to actually help the brain-computer interface? I mean, with Neuralink and these guys in Silicon Valley, I mean, that's going to happen. But so how can we either help so that ethically we do something which doesn't, make us some sort of hybrid between Terminator 4 and and a human being?
No, they actually brought a very important point, because with all this AI and Neuralink and all that, right, there's a scare that robots will take over and we'll be approaching the singularity and stuff like that. But whereas in a country like India with 1.3 billion population, that will be a disaster, if you have robots running around and taking over human jobs. Whereas the same knowledge of the brain can be used to improve people, to develop people further, to tap the so-called human potential. Right? How do we do that? So even that, everybody talks about it, how do you tap human potential, but there's no formula for it. You can't do it like that. So can we use all this knowledge and direct it towards improving people? Like that's what Lata is also talking about, not just diseased people. Right? Normal people who have certain problems, and it's not actually disease, but you want to improve, get over your inhibitions, get over your defenses, and that's again a huge question. Because as scientists, it's important to have an idea
we can
of what
become the best version of ourselves.
Yeah.
Sir, last year,
the best version of ourselves, whatever.
So last year, I was actually at MIT last July, looking at some of the advances that they were doing using a combination of all these. So they were looking at putting robots out for search and rescue for people who go get lost. That was one of the use cases. The other one, which I really found interesting, was they were looking at the muscle movement. So they were putting different sensors on the muscle, and when a human and a robot sit and collaborate on any work on the shop floor. So I work with some of the manufacturing industries, and the biggest challenge we have is where you have robots and machines on the shop floor. I cannot put people in because it becomes a high risk zone and I need to put them under protection. So in those cases, they were actually experimenting with, for example, lifting weights. If a human and a robot want to do that together, they had a student who had strapped in electrodes on his body, and he was flexing his muscle, and the way he's flexing and lifting it, the robot was matching him. Of course, they couldn't pick up weights at that time, and they couldn't do physical mobility along with the arm mobility, but they were looking at advancing some of those. So those are, if I look at it, it's really very, very useful. And the way I'm looking at self-regulation and goal pursuit is, if you look at harnessing all these neuroscientific potential on the shop floor. So I have teams who are working towards certain goals, and they have to meet certain targets and so on. But many times we get off target. So how do we stay on target? And is there a way in which we can help people figure it out themselves without being policed? And then at the end of the day, when we have robots on our team, so you may have a robot as a boss, or the other way around. You may have a set of people and a set of robots. So when you manage these kind of workspaces, how do you figure out how to get them to coordinate well? Because all of them don't have similar motivations to do certain activities. robots are just programmed while people have a different way of working through it. So these are some of the challenges that we've been looking at. So looking at brain activity, how does it translate into work on the ground in offices? I'm a part-time scholar with Professor Lata. So one of the things we do at work is also try to figure all these things out. And it's been quite challenging because getting that whole collaboration done. So we can actually take a problem statement which will make sense for neuroscientists as well as for behavioral scientists, and see how we can design experiments, gather data, which can be interpreted differently by both, but it will be at the end of it getting to some common use. So just a quick thought on that.
Oh, very nice. Yeah. So similarly, I think since we are all in academics, right, another big application area is education. So for example, in the Indian education system, traditionally it was a lot of rote learning, right? But now everybody is saying rote learning is bad. You need to use analytical methods. You need to have critical thinking and all that. But then some people say, no, rote learning is good for at a very young age. Now this becomes like a religion, right? What is a good thing to do? But whereas if we have better understanding of fundamental principles, laws of the brain, we'll be able to say decisively that at this age, this is better, and at some other age, something else is better. Right now, it's all a lot of hand waving, and it's a question of becomes a question of style, right? But whereas but that's not science.
Yeah, similar issue with the language in which you learn, right? I mean, the new education framework proposed, rightly or wrongly, because I don't know what is the supporting evidence. I like the emotion, but that you should learn in your native tongue till you are 5 or 6 years and then move to other languages. However, this is a big debatable topic. I mean, the same lines, rote learning versus critical thinking, native language versus common language, right? What are good and bad? I mean, from a cognitive development perspective, I mean, I don't see that at all in any of these debates. Right? I mean, what you are doing to the person should be compatible with their so-called hardware, right?
Yeah, correct.
Just to add more noise to this pool, we also don't have any sort of agreed on definition for what constitutes subjective experience, which is the big elephant in the room.
Yeah.
Right, I am seeing an object. It is very clear to me as a person. I am seeing the screen. It is not as if my brain is seeing the screen. I experience. So the experience combines my awareness. However, we do not have any theories of object recognition that have any space for subjective experience. Right? Whether a rat sees an object, a computer sees an object, a robot sees an object, or a human being sees an object, it is the same, right? But I think there is a deep disconnect when we are claiming we are modeling or we are understanding human perceptual or cognitive system, and you don't have any role for subjective experience in your theory, then I see it is disconnected from who I am.
So I think again we come to the same question. That is, in neuroscience has successfully collected all the important things in human life, put them in a basket, and have jettisoned it, have thrown it out somewhere. Right. This is one of and the question of experience, right? That's the first thing that if you look at the entire Candle and Schwartz, it never addresses this question anywhere, at least to my understanding, to my knowledge. Somebody can correct me if I'm wrong.
Yeah, I mean, Candle and Schwartz this is a classic example where there is no use for subjective experience.
Yeah.
But that's who we are actually.
Yeah.
Right? I mean, you take a visual perception system with small modifications. It is true for rat, it is true for macaque monkey, it is true for so-called human brain. But each of these animals have different experience of looking at an object.
Yeah, and that we don't have a good way to talk about. And the most important thing, most interesting thing. Now, looks like since the most interesting things are, I don't know, vague, we keep on giving ourselves busy something else, right? So that you don't feel guilty that you're not doing anything. Yeah, any other comments? Yeah, it's a difficult question. I mean, if it had been that simple, it would have been solved long ago. But,
Usually when we touch subjective experience, it's time to close the
well,
meeting.
pack up, yeah. That's right, yeah. But I think one of the best things is this, I don't know, people might have seen the book Universe of. I mean, that's a very good take on the whole subject. I mean, maybe there are others, but it's quite empirical. It's has roots in solid data, whatever.
Is that the beginnings or inspiration for this ITT?
Yeah, it is. Yeah, that's right. IIT. Yeah, information integration theory. Yeah, it has come out of this line of thinking.
Okay. Yeah.
So, yeah, the laws of the brain. So we made a list of it. It's there somewhere in my machine. I'm sorry, I'm not going to remember. See, one interesting thing that's happening recently is people have been showing that even simple deep networks can explain a lot of real brain observations. Because normally we thought that people always said, "Oh, deep networks are too stupid and too simple. Brain is so complicated and all that." But now you see paper after paper, appearing in top journals. That shows the power of even deep networks. But point is, deep network dynamics is a different story. I'm not sure how appropriate deep network kind of models how to explain brain dynamics, but at least simplistic, more average responses, right, for explain that deep network seem to be good enough. So the thing is, there's a lot of understanding at level of understanding sensory hierarchies, right? Then decision making, we have some good tools, from our reinforcement learning and things like that. But individual structures, like what does cerebellum do, what does basal ganglia do, and more importantly, I think we should keep asking the question why and not what or how. First of all, I mean, why do we need a structure like cerebellum? It is silent. We don't know if it contributes to experience. I'm not very sure. It's a very old structure and always kind of outside the brain proper, right? Like it looks like an attachment.
It is believed that if you remove cerebellum, you don't lose anything in terms of experience.
So why do we need it? Right?
The same. Oh well, you can say the same thing about the cortex.
Really? Yeah.
Yes.
Okay.
So there are half the cortex gone, and you are going about the world as usual. I mean, you take. Of course, there are changes. There are changes in personality and so on, but they are still aware of themselves. They are able to conduct their life. There are the recent Christoph Koch book on the experience of being yourself or something like that. It's built, basically explains the IIT theory.
Okay.
Gives what is the minimal substrate required for awareness or experience, subjective experience. So it turns out the hot spots in the posterior cortical area, something like inferior parietal lobe, precuneus, some of these areas are the important ones for experiencing yourself. And any other area, you take prefrontal cortex, for example. I was actually quite surprised that it is important for decision making and so on, but not for subjective experience. So there is damage to areas of the prefrontal cortex. For example, orbitofrontal, in the famous case of this the gauge, the guy who got a rod through the bottom of the brain, right?
Phineas Gage.
Phineas Gage, right? He didn't. I mean, he was not in a vegetative state after that huge insult to the brain, right? So it was functioning. But I have problem with these kind of things in the sense that it is not as if there is no change in the system. The person, people have reported anecdotally, the person who was Phineas Gage before the accident and after the accident is completely different. He is more volatile, aggressive after the injury, and earlier he was a peaceful, quiet man. Now, is that not a change? Right? I mean, okay, we talk about basic consciousness, awareness that is not disrupted. However, who he is as a person has completely transformed. And I don't know how does one accommodate those kind of things into. But that's the current take on what is the neural correlates of. So there is this word that is being used, neural correlates. It's a very cleverly crafted word in the sense that you don't say that this exists in this brain area, but these mediate that consciousness. So it is still possible that consciousness is actually a property of the world around, and you have a tuning device that allows you to experience, right? So this correlate is a very tentative word. It doesn't say, it's not the neural basis of consciousness, right? It's neural correlate of consciousness. But
so that brings even a much more tricky question, which is, why do we only talk about neural correlates? What about glial correlates? Because if you read, for example, Douglas Field's book, right, it's all glial cells. They are responsible for all the so-called neural disorders, right? They are underlying all neural disorders. So then, if you also look at the kind of things that we have been doing, the vascular contribution, then you should talk about vascular basis to everything. In fact, why not think of vascular dynamics as a basis to consciousness, right? Maybe pain is coming from that. If that is the case, then why not go deeper into the body? Look at the bodily system, because everything is a loop, right? Why do we draw the line and say experience comes from the brain alone, right? So why not we have a more systems level model that talks about how the entire body operates as a unit, and then why can't we have rigorous theories of experience that look at the entire body? Right, I think we arbitrarily draw a line and say that's all there is to it, and we really don't go deep into the question. Okay, I think any more comments? Because this is an open-ended problem, we can keep on discussing until tomorrow.
Hello. Yes.
Hello. Yes, Harsha, go ahead. You have a comment?
So, like, I wanted to bring up something like little different to what we were discussing. So, we have this recent improvements of deep learning and stuff coming into neuroscience. So,
Yeah.
especially when it comes to modeling human diseases and stuff, how reliable, like, how do we comment on the reliability of those models for actual application?
For diseases.
Yes, sir. Like when we want to describe the diseases and experiment on them, essentially, like how do we know they're reliable enough to?
So I know of only work where they applied deep learning networks to explain visual and auditory function, for normal function. There's a very nice review by McDermott, but I'm not aware of any work on diseases. Anybody has any idea? Raju or anybody? Deep learning applied to understand diseases?
yeah, so there are a couple of ideas for ASD versus typically developing versus autism classification based on structure and function of the brain. There is also ADHD, attention deficit versus typically developing. or you have normally aging versus mild cognitive impairment. These are posed as classification problems, and to the extent they are classification problems, the usual ML machine learning type of validation and those criteria hold good, right? I mean, you have a training sample, you have a validation sample to do model optimization, and then you have a test sample to out of that you have not used for training to validate, and you do this over k-fold, n-fold, 5-fold, 10-fold, any of these. So this as a classification question, it is posed as an ML problem, right? It's not no longer. Now, whether you get any insights as to what different regions specifically contribute to the disease is something that is still open, right? Whether works as a black box but doesn't give you any insight into what region might be responsible for typically developing, becoming a autistic sort of brain, right? So
Okay, any other comments? Should we slowly wind up? Because it's a very deep discussion. Right, anybody else? Stephane? Yeah, so then if there are no further comments, I think I want to thank the panelists. Yeah, go ahead. You have something to say?
Oh, thank you. I just wanted to thank you very much, because it was really motivating and stimulating. I was also wondering, maybe we could do something like, maybe you do it already, and my apologies if you do, but maybe we could try to do something like maybe a regular discussion together, but maybe also something like, these, I don't necessarily those social media, Instagram, Twitter, and so on, but maybe we could release some short videos, like 1 or 2 minutes, explaining a new paper that came out that's of interest maybe to students, so that we can generate maybe stimulate the community, because I'm trying to do that in my own area. It's kind of time consuming, but I have the feeling maybe this is the new way of connecting with people, and that I have to learn it. And it would stimulate me a lot, because this way, maybe we could reinforce the connection together, force me actually to get out of my comfort zone, because I think otherwise, if we're not constantly challenged, it's at least I know I'm not making progress if I don't force myself to challenge myself constantly. So that would certainly challenge me, and I would really like that.
That's right. That's a very good suggestion. In fact, we were thinking of something on similar lines. So Vignan has been, very, he was actively organizing soul conference and all that. I think we should also plan some kind of form a network of labs and have frequent kind of seminars. And whenever somebody invites some speaker, right, let that be available to the all the network of all the labs. Since everything is online, it's very easy to do that. Right, maybe we can fix a day every week, and have this discussion going on all the time in informal fashion. It doesn't have to do, so that we can really go deep into it and discuss threadbare all the issues. We can do that. I think let this workshop be like considered as a first meeting on those lines. But we can have simple 1 hour meetings, like once a week, and we'll call speakers from very different backgrounds. Right, just to understand how things are going on. So we constantly, like you said, we can constantly challenge ourselves. Right, so I think we'll make some initial plans, share the plans with you all, and then you can all make the suggestions. But we'll have the system in place very soon.
Right.
So this dialogue will be going on all the time. Okay, so thanks everybody, and hope people enjoyed it. It was very exciting 2 days. right? And let us keep meeting often and keep this conversation going. Right. So thanks a lot. Have a good evening.